15.2 Nerve Impulse, the Action Potential. All of our cells have what is called a resting membrane potential. Potential in this sense means a voltage. We can actually measure a voltage across the plasma membrane, much like we could measure voltage across the poles of a battery. The reason for this resting membrane potential is different distributions of ions on different sides of the plasma membrane. Specifically, it is sodium and potassium. The sodium concentration is very high outside of the cell. The potassium concentration is very high on the inside of the cell. Remember, ions are relatively impermeable to the plasma membrane, and anytime any of these ions do manage to slip across the membrane, the sodium-potassium pump is constantly working, and it will take 3 sodium ions and push those outside the cell, and then it will take 2 potassium ions and bring those back inside the cell. And so this creates different distributions of ions, and there are also more positive charges outside of the cell, more negative charges inside of the cell, and so this creates this potential. So at rest, that membrane is polarized. It has one positive side, one negative side, and we can measure this voltage or potential across the membrane. The inside of the cell is negative with respect to the outside, and we can actually measure about minus 65 or minus 70 millivolts across the membrane. So here's a very simple little diagram. This cylinder that I have here represents the cell. A lot of sodium on the outside, some potassium on the inside. If we measure to the voltage, we have that resting potential of about minus 70. Well, what if we open sodium channel, or really any ion channel? There are many different types of ion channels that can open and allow movement of these ions. So the simplest one perhaps would be a touch receptor. Touch receptors in your finger have sodium channels, and when mechanical pressure from touching something, that mechanical pressure deforms that channel and it opens, and it allows sodium to move down its concentration gradient. So if sodium moves down its concentration gradient, it's going to move from outside to inside. And so what would that do to the voltage across the membrane? If we start off at about minus 70 inside and we allow positive charge to come into the cell, that is going to make that potential less negative. So this would be a depolarization. Remember, polarization simply means charge separation. If we depolarize, we have less charge separation. We've moved it closer to 0. So sodium entering the cell might change that voltage to minus 50 millivolts. Well, really, we haven't accomplished anything. Very quickly, that sodium-potassium pump is going to pump that sodium back out of the cell, and this would be a repolarization event. And so things happen like this. This would be called a graded potential. We have very brief disruption of that resting membrane potential, but also very, very quickly, in milliseconds, the sodium-potassium pump is going to restore the resting membrane potential. But if that original stimulus, something touching our finger, is large enough and it lets enough sodium enter the cell, we can reach something called a threshold depolarization. A threshold depolarization is a larger disruption in the voltage across the plasma membrane, and it causes some different sodium channels to open. These are voltage-gated sodium channels. They will open anytime that voltage on the membrane reaches the threshold level. And whenever these voltage-gated sodium channels open, that initiates the nerve impulse, what we call an action potential. So here's our diagram once again. If we have a large enough stimulus so that we reach the threshold is normally minus 30 to minus 40 millivolts. At minus 30 or minus 40 millivolts, we open these voltage-gated sodium channels that allow sodium to enter the cell. Well, then there's going to be an adjacent portion here of this membrane that reaches threshold. And so we're going to open some additional sodium-gated channels. As soon as this portion of the membrane reaches threshold, we open the next set of sodium channels, and so forth. And so this action potential is some movement of ions across the plasma membrane. This occurs in the axon of a neuron, and it's simply a depolarization wave that moves the entire length of the axon. As one portion of the membrane reaches threshold, it opens sodium channels, allows more sodium into the cell, and so this is going to continue the entire length of the axon until it reaches the end of the axon. This depolarization wave or action potential can move up to 250 miles an hour. It is an all or nothing event, which means when we reach threshold and that first set of voltage-gated sodium channels opens, you cannot stop that action potential. It's going to continue the entire length of the axon. One action potential is not larger than another. They're all the same. We can measure this. And so this bottom diagram, if you see there about minus 40, that would represent the threshold depolarization. So in this diagram, they have the resting potential at about minus 65. If we allow some ions to enter and we ever reach threshold, that big spike that you see is called the depolarization wave. And so we're going to go from minus 40 threshold. We allow sodium to come into the cell. The inside of that cell can get all the way up to about plus 40. And this is because of the opening of these sodium channels. This happens in milliseconds, and so within about 3 milliseconds, those sodium channels begin to close. Also, whenever we get up close to the plus 40, the top of that spike, some potassium channels open. And those potassium channels will allow potassium to go down its concentration gradient, which would be to leave the cell. And as those positive sodium ions leave the cell, we begin the repolarization. And so that voltage across the membrane of the neuron is going to return back to its resting state. There's also a refractory period, and what this means is that after a neuron has depolarized, had an action potential, it will not respond again. It cannot initiate another action potential for several milliseconds. And what has to happen during this time is the sodium channels and the potassium channels have to reset themselves, and then also the sodium-potassium pump has to restore the ion distribution back to that resting state. So this refractory period is just a few milliseconds that it takes before the neuron could respond to another stimulus or initiate another nerve impulse.